Hello. Let's see. Get my speakers on. You should hear me. Um, should see the desktop, and you should hear me by now. And a lot of people to come in. Okay. Okay. First, I put this link up here, but the homework assignment's not there yet. It'll be up there later this evening. I'm still writing it. There's a homework assignment where you can use what we're talking about of transformations. So a homework assignment where you can do a simple example using transformations to get a sense of how they work. Okay, so that'll be up there later today. Okay, and what we're going to do today is go to this render and do some more examples. There's one thing we need to talk about that we haven't mentioned is how matrices actually work. We've kind of described matrices real abstractly. We say that we're going to use a matrix to move multiply a matrix times a vector and get another vector that moves the vector. Okay, but we haven't actually said exactly how a matrix works. So that's mostly what you learned in linear algebra. I mean, you should know matrix multiplication. Matrix multiplication is from linear algebra. So we're not going to really talk about matrix multiplication at all. But in linear algebra, you don't talk about so much specific kinds of matrices. Like they probably never even mentioned the rotation matrix in the linear algebra class. I know when I taught it, I almost never, the textbook didn't even mention the rotation matrix, because everything is done kind of so abstractly and they're not really doing anything with the linear algebra. They're just doing theory. You have no need for the rotation matrix. Okay, so we want to talk a little bit about the specific matrices and what they do, and we're going to see that that brings up a real important issue. Translation is a problem. When we want to move an object left and right, or just up and down, or forwards and backwards, there's something special about that operation. Translation is different than rotation. Okay, so okay, so first, yeah, well, here's rotation. This slide actually derives the formula for rotation really nicely. The rotation matrix is this matrix here. So you rotate by the angle theta with cosine theta, negative sine theta, cosine theta. And that's a two-dimensional rotation. It turns out that that's actually the heart of all rotations. Even three-dimensional rotations are really just a 2D rotation around an axis. So there really isn't exactly such a thing as a 3D rotation. Yeah, a 3D rotation is a 2D rotation around, so you're rotating, when you rotate around an axis, there's a plane perpendicular to axis where the rotation is really happening. The rotation happens in the plane, and all the planes simultaneously perpendicular to that axis. So it's a very special kind of, it's very two-dimensional like. So this is the matrix, and then these two slides derive it. Okay, and here's it's actually this does a really good job of explaining it. You're going to rotate this point to that point. So xy is the starting point, x prime y prime is the ending point, and this arrow hasn't changed length. You're just changing that angle. So you're going to change that point to that point, and so you're rotating by this angle theta. Okay, right. So then we want to derive these formulas for x prime, y prime. Okay, right. Now, if you actually look at those formulas, that's the matrix. See, he didn't write it out here, but if you do the matrix multiplication, you get cosine theta times x, negative sine theta times y. There's cosine theta times x, negative sine theta times y. Okay, so that formula there is the x prime in this multiplication here. And if you compute y prime in this multiplication here, you get this one here. Okay, all right. So this this shows you this is the idea of how we're going to derive that formula. Okay, so then it's done over here. This is the derivation. XY starts out with an angle phi. Okay, it's going to get rotated by the angle theta, but it starts with the angle phi. Okay, so then you write x in its polar coordinates. Okay, so the trick is to write x in polar coordinates. Instead of writing it as xy, you write it as angle radius. So you write it with radius r and angle phi. Okay, then x prime, write it in polar coordinates. Now its angle, its r is the same. See, it's got the same r, but its angle is the sum of these two angles. Okay, so its polar coordinate is the sum of those two angles. Okay, now the only trick is to apply a famous trig identity to that thing there. The angle, the sum of two angles. You apply a real famous trig identity. The angle sum trig identity. See if we can find a nice place. This one here. The sine of the sine of alpha plus beta and the cosine of alpha plus beta. You take those two formulas there. You take those two trig identities. You apply them here, and you get the formula we want. Then you're done. Okay. Okay. So you apply, well, actually you apply those trig identities, you get this, and then you convert this one from polar coordinates back to regular coordinates. Because see, if after you apply the trig identity, if you look, there is the polar coordinate of x, and there's the polar coordinate of y. So then, well, actually there's the polar coordinate of x, and there's the polar coordinate of y. So the trick is to take x, convert it to polar coordinates, take x prime, y prime, convert to polar coordinates, apply the trig identity to here, then convert from polar coordinates back to regular coordinates, and then you're done. Okay, so for convert to polar coordinates, apply a trig identity, go back to rectangular coordinates, and you have the formula. Okay, so it's a very cute little derivation. It's real simple. It's a real nice example of using one of the famous trig identities. There's all these trig identities, and you've seen them galore. And you don't actually all the time see actually uses of them. So you take a trigonometry class and you're asked to use them a lot. And then here's a real famous example of a really great application of one of those trig identities to derive this matrix for rotation. Okay. All right, so that's a quick derivation of the formulas for rotating a point around the origin. Well, we're going to see that you might ask, well, what if I want to rotate somewhere else? Here we're rotating a point where the center of rotation is the origin. Turns out that there is no other kind of rotation. You can't rotate around an arbitrary point, and we'll see what I mean by that. You can obviously you can stand anywhere in the room you want and rotate. Okay, but there's only the only matrix there is for rotation is around the origin. Okay, so if you rotate around some other point, like if you actually wanted to rotate around this point here, if you want to rotate around some other point, we have to do some tricks to get that to work. Okay. Okay, all right. So this is the rotation around the origin of a point. So you take the point, you're going to you're essentially rotating that arrow, the polar coordinate arrow of that point, and you're rotating that arrow. Okay, and if you want to rotate a point about any place else, we'll see in a little while how you have to play a special game, because the only matrix for rotation is rotation around the origin. Okay. Now, if you do 3D rotation, okay, 3D rotation, see, what it is if you rotate around the z-axis, remember the z-axis is the axis, in our way of doing, the z-axis is the axis coming towards us. So if you're rotating around the z-axis, you're rotating the plane of the computer screen, okay? And that's the xy plane, and there's the rotation of the xy plane. See, if you, this upper left-hand corner here, there's the 2 by 2 matrix for rotating the XY plane. And that's rotating around the z-axis. It uses the 2D rotation. Then this thing says that you're letting the z-axis stay put. Okay? All right. So there's a 2D, the rotation around the z-axis is a two-dimensional rotation of the XY plane and all the planes parallel to the XY plane. Then rotation around the y-axis, there's those four numbers again. And then there's the 1 on y, which says that the y-axis is staying put. And there's the 2D rotation of the XZ plane. See, it's the XZ plane. So you're in the X row, X column, Z column, 0, X column, X row, Z column, X 0, Z column. So you're rotating the XZ plane. Okay. So you're doing a two-dimensional rotation perpendicular to the y-axis. And then same for rotation around the x-axis. There's the two-dimensional rotation of the YZ plane. So you're rotating the YZ plane and everything parallel to it. All the planes parallel to YZ are rotating in a two-dimensional way. Okay. All right. So there's our three basic rotations in three-dimensional space around X, Y, and Z. Now, the Earth doesn't rotate around the X, Y, or Z axis. The Earth rotates around its own axis, which is not the X or the Y or the Z axis. So how do you get rotations around an arbitrary axis? Okay, and that's a really crazy formula. Here it is. Okay, which we're not going to try to derive this. You can look up the Wikipedia page for it. It's got a name. It's called Rodriguez's formula. Okay, but what you do is there's the coordinates of the rotation axis, and then there's the angle you're going to rotate by. Okay, so these three numbers are and you can see they appear all over the place. Those three numbers are the I, J, and K of that vector. Okay, there's the I components, J components, and Z components, the X, Y, and Z components of that rotation vector. And then this C here is the cosine of that angle, and the S's here, everybody uses this abbreviation to make the formula a little bit more readable. You let cosine of theta be C and sine of theta be S, and then you write C's and S's in this formula. Otherwise, you get cosine theta, sine theta all over the place, and it becomes even harder to read. Okay, all right. So you can do an arbitrary rotation around an axis and an angle. Okay. But for the most part, in computer graphics, it turns out in the majority of cases in computer graphics, it's good enough to use a rotation around X, Y, or Z. Okay. So you can, this will get you real far, these three rotations, and every once in a while you need this rotation. Okay. And the renderer has all four of them. The renderer has that one, and it has those three. But the vast majority of applications only need a couple of these. Most of the time you can think of things as being rotating around X, Y, and Z axis. Like airplanes are thought of that way. They call that roll, pitch, and yaw. Okay, they use those three words. They actually, people in airplane world have their own words for these three: roll, pitch, and yaw, meaning rotation around an x-axis, a y-axis, and a z-axis. Okay, so you can get real far with just these three, and then occasionally you need this one. Okay. Okay. So that's rotation. Okay. Okay. Now let's talk about translation. Translation is the tricky one. Okay. Translation isn't a matrix operation. It's a vector operation. Okay. So let me draw a picture. Let's see. If you create a two-dimensional axis, a two-dimensional plane, okay, you can I don't know if I probably can't draw. Oh, I can draw a point by maybe making a tiny little circle. Okay, there's a point. Okay. If I want to translate, now the point has got coordinates x, y. Okay. And I want to translate it, say, this way. Well, actually, I'll just translate it to over here. Okay, so I translate it from there to there. So that would be a point x plus a, y plus b. Okay. And what I've really done is I've done, if I called this point, well, let's see, will be what I've really done is x comma y plus a comma b. I've actually done vector addition. To get from here to here, that's vector addition. Okay, x plus y. Okay, and yeah, vector addition is component wise x plus a comma y plus b. Okay, so that's pretty, there's nothing deep there. Okay, but the thing is, you can't get a matrix to give you this result. There's no matrix that's going to give you this kind of an answer. Okay, if I do, let's see, a matrix operation over here. Let's see. So okay, there's the 4 numbers in a matrix, and I'm going to multiply it by a vector x, y. Okay. What you get is, okay, a 0, 0. Let's see, times x plus a 0, 1 times y. Okay. And here you get a 1, 0 times x plus a 1, 1 times y. Okay, that's matrix multiplication in a 2D case. Okay, now notice that there's no way to add a constant to x. Okay, see, only thing you can add to x is something that depends on y. See, on the right-hand side here, I want x plus a constant. Okay, and I want y plus another constant. But over here, I get x plus some multiple of y. There's nothing else I can have on, besides x. I have to have some multiple of y. And in the second row, I have to have y plus some multiple of x. I can't just have y plus some other constant. Okay, so my input should be, see, there's no way, so another way to put that, there's no way that this can equal what we have here. There's no way this cannot equal, x plus some constant a, y plus some constant b. Okay, there's no way it can be equal to, okay, there's no way I can get that to equal this left-hand side, because I could make a1, I can make this guy a 1. If I make this guy a 1, I get 1 times x, which is x. Okay, but there's really nothing here that I can put here that would give me this a. Yeah, if you said make y 1 and then there's the a, but then you've lost your other point. See, then you're forced to make y 1. So so you can't, the y is your input. It's not something you're allowed to change. So you can't get this thing to equal x plus a. And you can't get this thing to be y plus b. Okay, translation cannot, it's not a linear operation. It's got a name, translation is called an affine operation. Translation is not linear. Instead, translation okay, it's affine. Let's see, did I get it's not a linear operation. So translation is not a linear operation. Translation is an affine operation. Okay, right. But we can turn it into a linear operation. We can turn it into okay. Linear operation means there's a matrix for it. Okay, affine means something else. Okay, so translation is not linear. There's no matrix for it, but instead it's something called affine. Okay. Actually, what affine means is a more general formula. Linear means that you have a matrix A times a vector X. Okay. Linear means matrix times vector. Okay. Affine means, here's what it actually means. It means matrix times vector plus vector. It's like mx plus b. Okay. Matrix times vector plus vector. Okay. That's what affine means. Okay. Linear means just matrix times vector. Affine means matrix times vector plus vector. Notice that this is mx and this is mx plus b. The matrix plays the role of m. It's kind of like the slope of something. You know, the numbers in the matrix are kind of like generalized slopes. Okay, so this is m times x. So linear means a line through the origin. You know, the y-intercept is 0. Affine means in one dimension. Linear means a line through the origin, and affine means a line not through the origin. There's a y-intercept. Okay, so translation is an affine. Translation is this is the identity matrix, and you're just adding on the translation vector. Okay, so that's what we have over here. You have an identity matrix here, and you're just adding on what we would call the translation vector. So B is the translation vector. Okay, all right. So AX plus B is affine. And one of the reasons why this is horrible to explain to students is because math books are written in a way, they're stubborn. They're really written in a stubborn way. You're taught that y equals mx plus b is a linear equation. So, you know, that's the equation of a line. But it's not a linear equation. It's an affine equation. It's eventually, at some point, if you take enough math classes, the professor walks in the room and says, you know, we've been giving, you know, you've been told for, you know, all your life the wrong name for this thing. This is not, it's not linear. It's affine. Okay. What's linear is y equals mx. This is the one that's linear. Okay. So if you want to generalize to what we're learning, you know, what we're doing in linear algebra is this is the linear equation, and this is the affine equation. This is line through the origin. This is an arbitrary line. Okay. And for some reason, the name stuck that this is the linear equation. And then you get to linear algebra class, and it's no longer the linear equation. You get to the linear algebra class, and the equivalent ax plus b is not linear. It's called, and now you have to change the name, because in a linear algebra class, it's all about linear operators. So you can't call this one linear. You can't call this linear in linear algebra class. So you have to give it a different name. And it's called affine. And it causes confusion year after year after year. It causes confusion to all kinds of people, that all of a sudden what you were calling linear stops being linear and starts being this other name, affine. Okay. All right. So translation is not linear. Translation is affine. Okay. But there's a real famous trick. Let me save this. There's a famous trick that makes translation into a matrix. Okay. So there's a trick that makes translation into a matrix. But the trick is, okay, let me show you what the trick is. Okay. Here's the trick. Okay. Replace vectors like this with vectors like this. Okay, so we're going to replace every vector xy with a vector xy1. Okay, we're going to tack an extra 1 on every vector. This is called a homogeneous coordinate. Now notice that I'm still in 2 dimensions. So this is 2-dimensional homogeneous coordinate. Now it looks like I'm in 3 dimensions, and I am, but it's a special case. The third coordinate is always 1. Okay, so this is 2-dimensional, and this is 2-dimensional homogeneous. So this is a 2-dimensional coordinate. Okay, and I'm going to replace the 2-dimensional coordinates with 2-dimensional homogeneous coordinates, x, y, 1. And I'll also do the same thing in, eventually, we're going to do this first in 2D, but we'll also do it in 3D. So we'll replace vectors like x, y, z, which is a 3D coordinate, with x, y, z, 1, which is a 3D homogeneous coordinate. Okay. Now, here's why that works. I want to take x, y, plus a, b. That's my translation. Translation, let me write this way. Translation of xy equals xy plus ab. Translation of a point by a vector. Okay. Okay, so that's translation. Translation of a point by a vector is just to add the vector on. Okay, right? And if I wanted to write that more compactly, I would say translation of v is just v. Oh, no, I'm sorry. Translation of a vector. Yeah, translation of a vector v is v plus a vector a, something like that. Translation of v is v plus a. If I was using vector notation, I'd say translation of vector v is just v plus the vector a. Okay, so here I've written it on components, and here I've written in vector notation. All right, this is the affine. See, there's the affine. Yeah, if I wanted to put a matrix in there, there's the identity matrix. Okay, so it's I times v plus a. Okay, so there's an identity matrix in there. So this is the affine case. Okay, but here's what I'm going to do. I'm going to change it to being I'm going to change it. I'm going to switch over to the homogeneous coordinates. Okay, but then I'll write it in matrix notation. Okay, so here's what I'm going to write: 1, 0, A, 0, 1, B, 0, 0, 1. Okay, there's my translation matrix. Okay, this guy here is going to be the translation matrix, and it's going to translate the vector x, y, 1. Okay, so I'm going to, instead of translating this 2D coordinate, I'm going to translate this 3D coordinate. So I'm going to use this translation matrix here. So now I'm going to say the translation of x, y, 1 is, okay, so the translation of xy was this. The translation of xy1 is going to be this. But now do the matrix multiplication. Now, so this guy here is this is the translation matrix. Now do the matrix multiplication. I'll get 1 times x plus 0 times y plus 1 times a. So I'll get 1 times x plus 0 times y plus 1 times a. Okay, which simplifies to x plus a. And the next one I get is, so I do the, now I'm going to multiply the middle row by that column. Now I'll get 0 times x plus 1 times y plus, what am I, b times 1. Notice I did, if I read across the middle row of the matrix, down that column, I get 0 times x plus 1 times y plus b times 1. Okay, but that simplifies to, y plus b. Okay, and then the last one, okay, I'm going to multiply this row times that column, and I'll get 0 times x plus 0 times y plus 1 times 1, and I get 1. Okay, notice that I got the homogeneous coordinate of this guy. Yeah, the homogeneous, let's see. So I got the homogeneous coordinate of that guy. So the translation of xy is x plus a, y plus b. And there it is, x plus a, y plus b, but I get the homogeneous coordinate of it. So I take the homogeneous coordinate of xy1, and I get x plus a, y plus b, 1. Okay? All right? So this is really amazing that translation turns into a matrix multiplication if you go up a dimension from 2 dimensions to 3 dimensions, but you keep the third coordinate always 1. Okay? So you keep the third coordinate always 1. And then you could do the same thing in with 4x4 matrix and do translation of a 3-dimensional vector. You can do translation of a 3-dimensional vector. Okay, so you could do this whole thing over again. Starting with this, and you could do the whole thing over again, just more to write. You could do the whole thing with vectors of length 3, replace them with vectors of length 4. Okay, all right. So there's the part we wanted. See, there's the adding on to x and y. It's really this guy down here that helps us a lot. You know, this extra one here, remember this extra one, see this extra one down here, it caused that plus A, that plus B, okay? Oh, let's see. I should have wrote this as, if I keep the right, or A times 1, because A is coming from the left. So that's A times 1. So if I kept the, yeah, I try to be careful about the order, not that order matters, multiplication is commutative, but see, that was A times 1. Okay, so it's this one here is that one down there. That extra one in the lower right-hand corner of this 3 by 3 matrix is kind of like a little magic thing that's doing the translation for us. Okay, but then we also need these guys to have an extra one in them. So that one has extra one, and then we get an extra one over here. Okay, but we've turned translation into a matrix operation. Okay, computer graphics people love this. So all modern 3D graphics is actually done in 4-dimensional space. Everything is done in homogeneous coordinates. Okay, and your graphics cards multiply 4 by 4 matrices. They can multiply 3 by 3 matrices, but the real work is to multiply 4 by 4 matrices. Okay, so if we go to this folder on rendering, go back here. Okay, here's the 3D transformations. The 3D transformations now are 4 by 4 matrices. Okay, because we want to do translate. See here's the translation amount. The translation amount, say, wrote delta x, delta y, delta z. This piece here of the 4 by 4 matrix, that's where the translation is. This 3 by 3 region over here is where the rotations show up. See, the rotations show up in this 3 by 3 section over here. Okay, and see the rotations showing up in this 3 by 3 section here. The rotations showing up in this 3 by 3 section here. And you see here, these are all 0 because this is a pure rotation matrix, so it doesn't have any translation in it. You can mix rotation with translation. If you put numbers in here, if you change this from a 0 to something that's non-zero, then you're combining a translation with the rotation. Okay, and similarly, if you go back over to here, if you change these numbers to be, see that right now this is the identity matrix. This 3 by 3 part here is 1, 1, 1 with zeros everywhere else. So that's the identity matrix. So there's nothing else but translation here. If you change those 9 numbers, then you're combining translation with something else. Like you could put a scaling here, then you would have a scaling and translation matrix. Okay, all right. So these are the matrices that we use. We use these 4 by 4 matrices. And the reason we use 4 by 4 is so that it's this one here forces us to go into 4 dimensions. Okay, yeah. The scaling and rotation don't need the 4th dimension, but translation does. Okay, and then there's an interesting question about, like, why bother then if rotation doesn't need a 4th dimension, and scaling doesn't need a 4th dimension. Only translation does. Why add this extra coordinate to every? It takes up a lot more memory. You know, matrices are now 16 numbers instead of 4 numbers. Every vector is 4 numbers instead of 3 numbers. If you have a scene with millions and millions of vectors, you know, every vector now is 1 extra double. Yeah. So if you have millions of vectors, you actually have megabytes of extra data. Okay. So is it worth all the extra data? Why not just switch between addition for translation and multiplication for rotation? Okay. Why not just have, and the answer is, here's the reason why. Suppose you wanted to transform a vector, and you're going to transform it with a whole bunch of matrices. So matrix 1 times matrix 2 times matrix 3 times matrix 4 times matrix 5. Okay. Well, actually, let me rewrite. Suppose it's going to be a rotation followed by so there's a rotation followed by a translation, followed by another rotation, followed by another translation, say, followed by a scaling, followed by a translation. Okay, suppose that's what I was doing to the vector v. Okay, so the transformation of v is to translate it, then scale the result, then translate the result, then rotate the result of that, then translate the result of that. Okay, now if you do these with 4x4 matrices, if I'm going to put grouping around here, you do that. You do that first. Then you're going to do that. So if I think of it as grouped, first you translate it, then the result gets scaled. Then the result gets translated. Then the result gets rotated. So if I write it as a composition of functions using that kind of notation, you're working from the outside in. You're working from the inside out. Okay, you start here, do that first. Then when you've got that result, you do that next. Then when you've got that result, you apply that to it. Then when you've got the result of that operation, you apply that to it. Okay. Oh, and then there's one more to do. Okay. Now, if these were matrices, I would do this as R1 times T1 times R2 times T2 times S1 times, oh, that was a T3, third trend, T3. Okay, see, if I'm using matrices, I would multiply all those matrices first, then apply to vector. Notice that changes the order of operations. Instead of applying this thing to V, getting a result, then applying this to it, getting a result, then applying this to it, then getting a result, okay, you would try and make these things more readable. I'm not sure what makes, oh, I had an extra. To make it more readable, you take this matrix on that vector, you get that answer, and you let S1 act on it, and then you let S2. Okay, so then you would, you do this first, then that one on the result. Now this says take the product of all those matrices first, then apply it to this. Okay, that's way more efficient. Okay, that does, because remember, this would usually be done in a loop, and this would be vertex I. This would be the ith vertex in a loop, and you might be doing this loop on 1,000,000 vertices. Okay, so it's better to do this ahead of time, and then apply a result matrix M to Vi. Okay, so M is just this result matrix. So then you do this multiplication ahead of time. Okay, now suppose I didn't use these. Suppose I did rotations with a matrix, translations with addition, rotation with a matrix, translation with addition, scaling with a matrix, and translation with addition. Then I couldn't use this trick here. I would have to actually do this. Literally, I would be stuck doing it this way all the time. I'd have to use the matrix. I would have to use the addition part of the CPU to do that operation. Then I'd use the matrix multiplication part to do that operation. Then I'd use the vector addition to do that operation. Then I'd use the matrix multiplication to do that operation. Then the vector addition to do that operation. So I'd be switching, the computer would have to switch between doing a matrix operation with a vector operation, and a matrix operation and a vector operation. And would have to do that for every one of the vertices, as opposed to pre-computing this one matrix and then applying it millions of times. Okay, so that's what somebody figured out about 40 years ago. You know, and very early in the days of computer graphics, they realized that if they turned the translation into a matrix, then this sequence of events could be turned into one matrix operation. Okay, and that one matrix operation is way faster than this sequence of operation of addition for translation, multiplication for scaling, addition for translation, multiplication for rotation, addition for translation, multiplication for rotation. Yeah, that would just be way too. Well, I mean, the very first graphics computers probably did that way. Yeah, they probably at the beginning. I'm not sure exactly when someone figured out this trick. It may have been right away because they were very smart people. So they may have just immediately realized, because homogeneous coordinates have been invented by mathematicians over a couple hundred years ago. So mathematicians knew this trick. And if the people in graphics were really well educated in math, they would have known that there's a trick for converting translation into matrix multiplication. So they may have known the trick right from the start.
Isn't that kind of, oh, sorry.
Yeah, go ahead.
I was just going to say, isn't that what Einstein had to do to unify some forces back in the day, was add the dimension of time?
Yeah,
and then his equations worked?
Yeah, but for a completely different reason.
Right, but it's really similar. That said correct, but it's really similar.
Well, yeah, but yeah, changing dimensions solves problems in a lot of, there's a lot of places where changing the dimension of the problem helps. Okay, Einstein changed from 3 dimensions to 4 dimensions by adding time. Here, the 4th dimension doesn't have this. In this case, this 4th dimension doesn't have a name. It's what's called the homogeneous coordinate. It doesn't represent anything. So this is one thing that's really different. Like Einstein added time to the x, y, and z. So you have space, time, 4-dimensional space. Here, that 4th coordinate, it's usually called W. Okay, it's x, y, z, w, but w is always 1. It doesn't even have a name. I've never seen anybody name that 4th coordinate. You have the x coordinate, the y coordinate, the z coordinate, which are your 3 spatial coordinates, and then w. Yeah,
if you named it, you could call it unity for 1.
Well, in some situations it's 0.
Oh, okay.
Yeah, we'll see that we kind of switch. That sometimes it'll be a 0. It'll be a 0 when this thing represents a vector, and it's a 1 when this thing represents a point. Okay, and there's a slide here to show you that. In this, okay, see this thing that says, oh, not that one. There's this idea of what's called homogeneous arithmetic. Okay, a vector has a 0 in the 4th slot. Okay, a point has a 1 in the 4th slot. Okay, now, so this would be xyz 0, xyz 0. Notice that if you add 2 vectors, you get a vector. If you subtract 2 vectors, you get a vector. Okay, if you add a point to a vector, you get a point. That's translation. So you're translating a point by a vector, and you get a point. Okay, and here's an interesting, if you subtract 2 points, you get a vector. That's the vector that displaces from one point to another. Okay, now see, these ones in red aren't allowed. You don't add points. Points aren't algebraic things. Points are positions. You can see if you add 2 points, you get a 2 down here. And what's supposed to be down here is either a 0 or a 1. 0 meaning vector, 1 meaning point. So if you add 2 points, you get something that's neither a point nor a vector. So that's not allowed. Same, you don't multiply a point by a number. You multiply a vector by a number. You don't multiply points by number. So this little scheme is called homogeneous arithmetic. And it allows for two kinds of homogeneous vectors, or two kinds of homogeneous vectors: points, which have a 0 in the fourth slot. I'm sorry, vectors, which have a 0 in the fourth slot, and points, which have a 1 in the fourth slot. Okay.
So does that have anything to do with the fact that vectors have a direction and points don't? Is there some relation there?
No, no, no. It's no, because what it is that there's an algebra for vectors. Vectors
Okay.
are things you add, points aren't.
Got it.
So the idea is that points are places in space. Vectors represent things like forces and displacements. So you can add two vectors, but you can't add 2 points. Now, in your linear algebra class, if you go thumb through your linear algebra book, you're going to find a place in it where they say that points and vectors are the same thing. In a linear algebra class, we don't make a distinction between points and vectors. A vector is a point, and a point is a vector. So in linear algebra class, when you're working with these kinds of things here, xy can be thought of as a point, or xy can be thought of as a vector. Okay. When we switch to homogeneous coordinates, when xy is thought of as a vector, we make this one a 0. When xy is thought of as a point, we make this a 1. So in 2D coordinates, we say that vectors and points are the same thing. And every linear algebra book somewhere makes that statement that vectors and points are the same thing. But when we move to homogeneous coordinates, it's convenient to make a distinction between vectors and points. Vectors are xyz1 or xyz0, and points are xyz1. Okay. Notice the columns of this matrix are what? Look at this first column. Okay, go back to, it's easier to look at this other picture. Look at that column. What would you call that column?
A vector?
No, because look what's at the bottom of it. Oh, yeah, it's a vector because
Okay.
at the bottom is a 0.
Okay.
Yeah, and this is a vector, and this is a vector, but this is a
Point.
point. The last column is a point. Okay, so there's a weird thing going on here where the matrix is a mixture of 3 vectors and 1 point. And all of these have that property. Because the bottom row is 0, 0, 1, there's 3 vectors and a point. What that represents is, this picture here, that this matrix represents a coordinate system where this column is the origin of a new coordinate system, and this column is that basis vector, and this column is that basis vector. Okay. Now, that's a way of thinking that we don't really need to use. It's mentioned in here, but that's how people start thinking. They have 2 kinds of things. We have vector things and point things. Vector things have a 0 in the 4th coordinate. Point things have a 1 in the 4th coordinate. Okay. In this case, it's the 3rd coordinate because this one's doing things in the plane. And then a matrix is kind of a weird mixture of vector columns and 1 point column. And that's so that you can think of the matrices this way as representing a coordinate system. Okay. All right. So this stuff, people are not afraid to use real mathematics in the real world. The computer graphics people, they weren't afraid to say, oh, 4-dimensional space is convenient. Let's work with it. And we'll build a $1 billion industry of graphics cards around 4-dimensional spaces. Okay, so all graphics cards are designed to do 4 by 4. They do 4 by 4 matrix arithmetic. Okay, real fast. Graphics cards are basically designed to do 4 by 4 matrix arithmetic real fast. And again, it's only because of the translation. But like we said here, you do it for you need to make this leap for the translations, because otherwise you're going to be stuck doing this weird thing of vector addition, then matrix multiplication, then vector addition, then matrix multiplication, then vector addition, then matrix multiplication, which will slow you down by a huge factor. If all of them are matrix multiplication, you can just multiply the matrix once and then apply the matrix over and over again to the input vector and never have to do this matrix multiplication ever again. And then you're doing this one matrix multiply on every vector instead of these gazillion operations here over and over. Okay, so it's worth converting everything to homogeneous coordinates because of the translations. Yeah, the translations kind of bump you up into 4 dimensions. Okay. Now it turns out that there's something else going on here that we won't have time to get to, but you can do projection with 4x4 matrices also. So at some point, the graphics people realized that going up to 4 dimensions actually makes clipping and projecting easier also. It turns out that your graphics card does clipping in 4-dimensional space. And that was for a different reason than this translation thing. It turned out that 4-dimensional space turned out to be a beautiful place to do graphics in because it did 2 things. It speeds up translation and transformations, and it also speeds up clipping. It turns out that you can do clipping in 4-dimensional space, and that has almost nothing to do with this translation stuff. It's just another reason why 4-dimensional space is a good place to do computer graphics. It makes the clipping algorithm work better. So the clipping algorithm also ends up being done in 4-dimensional space. Okay, all right. So, oh, not here. So all our all our matrices. Now we're not going to work with 3x3 matrices. The 3x3 matrices representing 2-dimensional transformations are just a stepping stone to the 3x3 matrix, the 4x4 matrices, which do 3-dimensional affine transformations. So everybody in computer graphics introduces these ideas with 2-dimensional transformations because it's a little bit easier to draw pictures and write down the matrices. But the graphics cards do the 4x4 case. So everybody starts off talking about the 2x2 case, especially with the rotation, because it's a lot easier to do the rotation in the 2x2 case, in the plane. But the graphics card does everything in 4x4 matrices. Okay. Now, if we go to the renderer, in this renderer, the vertex has been changed to 4 numbers. Okay. So then when you build a vertex, you get 4 numbers with a 1 here. The default vertex is the origin. The default vertex is the origin, which is 0, 0, 0, but it's a point, so it gets a 1 there. So the vertices always have a 1 here. Now there's also a vector class now that wasn't there before. The vector class has x, y, and z, and it allows there to be a 0 in the 4th coordinate. Okay, so now there's going to be a vector class and a vertex class. The vertex class will have a 1 in the 4th coordinate, and the vector class will have a 0 in the 4th coordinate. Okay. Okay. So now the render separates the vertex idea from the vector idea, but they're both homogeneous. They both use 4 numbers. Okay. Now the vertex class, some graphics cards for their vertex class don't even have a W there, because it's always going to be 1, so you don't really need to store it. But I went ahead and did it with a W there. I put the W in there. It won't actually, occasionally you'll see there's a couple steps where it can be something other than 1. There is a reason why it might be other than 1. But some graphics cards, they don't actually put a 4th, for the vertex, they don't actually put a 4th number. They try to save a little space because the 4th number is implied to be a 1 all the time. So then when they do their matrix multiplications, the hardware has to introduce that 4th number kind of arbitrarily to, well, it's not stored in memory, but it's kind of built into the hardware. But here, to keep things kind of easier, the vertex has 4 coordinates. There'll almost always be the case that that fourth coordinate is going to be 1 for a vertex, and it'll be 0 for a vector. Okay? Then the matrix class is made up of 4 column vectors. See, if we think these pictures, a matrix is 4 column vectors. Okay? So it's going to be column 1, column 2, column 3, column 4. Some people store their matrix as 16 numbers. And I went back and forth, and I thought it's a little bit easier to write the code in terms of 4 column vectors than it is to write the code in terms of 16 numbers. So the code ends up being a little bit easier to write, okay, and a little bit easier to read. So you can see sometimes here's the 16 numbers. You kind of see them anyway. Yeah. But the 16 numbers are in 4 column vectors. Okay. So some people will write this matrix class as made up of 16 numbers, and some people write it as made up of 4 vectors. Okay. So I chose the make it 4 vectors. Okay. And then this class implements matrix multiplication. So it lets you multiply matrix times matrix, matrix times vector, matrix times vertex. So it does all these different operations. Okay. See, there's matrix times matrix. There's, let's see, there's matrix times vector, and there's matrix times vertex. Okay, so matrix times vector returns a vector, and matrix times vertex returns a vertex. Okay, so all the possible combinations are in here. Matrix times matrix, matrix times vector, matrix times vertex. Okay, so that's done in the matrix class. Okay, now, and then like we saw in class on Tuesday, we use these now to move vertices around. We use the scene graph to represent. Remember, we talked about the idea that we're declarative now. We don't actually do the moving of a vector. We let the renderer do it. So remember, this is what our scene graph looks like. Okay, yeah, the scene is a list of positions. Each position is a matrix that says where that model belongs in front of the camera. So the model, I never change the models. The models are almost always centered at the origin. Okay, so like if you give me a model of a sphere, I'll have the sphere centered at the origin. A cube, the cube will be centered at the origin. Even a cow, the cow is probably more or less centered at the origin. Okay, so the models hold vertices, and the models are usually centered at the origin. Then this matrix declares that it says this is how you would translate all the vertices in this model to put the model in front of the camera. Okay, but that's not done by us. We just build this scene graph. So we're declaring that model is going to be translated to the right. This model is going to be translated to the left. This model is going to be rotated. Okay. So that would put our 3 models in front of the camera. One slightly moved over to the left of the camera, one moved to the right, and one that's rotated. Okay. But the models are really the models themselves, as far as they know, all their vertices are set up so that the model is sitting centered at the origin. Now, remember when you did the PNW models, they had one corner at the origin. You don't always center your models at the origin. Sometimes it's convenient to put the origin at one corner of the model. So the PN and W, like letters, it's real common for letters to have the origin at one corner of the letter. But for models like spheres and cubes, it's usually easier to have the origin at the center of the model. Okay. Then when you want to put the model in front of the camera, instead of changing the vertices in the model so that it's in the right place, we just pair it with a matrix that describes how that model should be moved. Okay, that's real important. This thing just says, this thing, so it's like a hint. It's like saying, this is where I think that model should be. Okay, now what happens then is that the renderer, the very first step of the renderer, we go look at there's a new pipeline stage in the renderer. The first stage of the pipeline is to multiply that matrix, to do the matrix multiplication. See, there's this model to view pipeline stage. Okay, the model to view pipeline stage is this one. What it is, the way to think about it is, oops. The model, all its vertices are relative to its origin, to its center. Okay. The camera is the one, but the camera is at the center of the world. So we need to move this model so it's not, if we left the model sitting at the center with its center at the origin, the model would be on top of the camera. So we need to eventually somehow move the model using this matrix. So that's the first step of the render. The first step of the render is to move you from the model coordinate system to the view coordinate system. You're putting the model in front of the camera. So you're taking every vertex in the model and changing it from its model-based coordinate system to the camera-based coordinate system. That's what this matrix does. So this thing multiplies each vector vertex in the model with this matrix. And that's the name given to this. This is the model matrix. See, that matrix is associated with that model. So in the code, it's called the model matrix. Okay. So now, what you do is the renderer, the renderer walks this list. It goes to this position in this list, and it multiplies this matrix times every vertex in that model. Okay, and that creates a new list of, what that does is it creates a new list of well, actually what this one's doing is this one's right now set up to mutate the vertices. So what it does is, it applies this matrix to every vertex in this model and updates the vertex. So the model gets all its vertices updated. So before doing that, the render makes a copy of the model. It actually does this on a copy of the model. Right now, the render starts off by making a copy of the model. So this is model 2. Because if I move the model itself, when the model was given back after the render was done, after the render is done, you don't want this model changing, because this is your game, this is your scene. You want to, if you want to move this model, you want to change this matrix from one frame to the other. If you're going to make this model move from one frame to the other, you want to change that matrix. The renderer, though, needs to put that model in front of the camera. So the renderer needs to change that model. But since you don't want to change that model because it belongs to the person, the game, the renderer makes a copy of that model and actually moves the vertices in the copy. So the render starts off by making a copy of the model. Then it can start mutating all the vertices in the copy of the model. Okay, so then it goes over here and it sets the vertex in the model to be the vertex times the matrix. So it takes each vertex, multiplies it by the matrix, and then mutates the vertex to be equal to that transformed one. Okay, so it mutates every vertex to be updated with this transformation. That puts that model in front of the camera. Okay, but that happens inside the render, and it's actually happening to the copy of the model, so that this graph just stays the same. You give this graph to the renderer, and when the render is done, you get this graph back. Nothing's changed. The renderer uses that graph to paint the frame buffer, and it does a lot of work, but it does the work on a copy of that model, a copy of that model, a copy of that model. Then when the render is done, the copies are garbage collected. Okay, so the render applies that matrix to a copy of that model. That puts the model in front of the camera. Then it can be projected to the view plane. Okay, then it puts this model in front of the camera. Then that model can be projected into the view plane. And then it puts this model in front of the camera. Then that model can be projected. And then after they're projected, they can be rasterized. And then after they're rasterized, they're put into the frame buffer. Okay, so you move them in front of the camera, then project them to the image plane, then rasterize them to the frame buffer. Okay, and then garbage collect the model, because the model is a copy of the original one. So after you transform this model in front of the camera, then you transform this model again to be in the image plane. Yeah, you project that model to the image plane. So then you mutate that model again. Then after you projected that model to the image plane, that's see, this one projects the vertices into the image plane. See how it's mutating the vertices. Okay, right now that's not done with, this projection is not done with a matrix. And later on it can be done with a matrix. Right now the projection is done with these formulas that we learned. Okay, but notice that it's updating each vertex. So we're projecting the vertex from three-dimensional space into the two-dimensional plane, the image plane. We're projecting into the image plane, and we're modifying the vertices, which are the copy of the model. So we're doing this in the copy at this point. So this is mutating the copy of the model. Okay, all right. So, and this matrix, the key is that, remember, it's been if we want to do something like take this model, translate it, rotate it, scale it, then translate it, all that's encoded into this one matrix. That one matrix can hold as much information as we want. So there can be a lot happening to that model, but it's all in that one matrix. Same with this model. This model might be scaled, then translated, then rotated again, but all that's buried in that one matrix. Okay, and we saw in class the other day how you could, if you just pre-multiply these matrices together, we saw it in this example. See, you just see, there's where you're building that matrix that goes into the scene graph. See, that matrix can hold a bunch of, that one matrix can be the result of taking a product of a bunch of things. So my model is going to be translated, rotated, and scaled. But all that's I do that multiplication before giving this scene graph to the renderer. Before giving the scene graph to the renderer, I do this multiplication here. I build that matrix there. Then the renderer will take that resulting matrix and multiply it by this square. And it'll take that resulting matrix and multiply it by that square again. But notice that that square is in this tree twice. So there'll be so the first step of the render is going to make two copies of this square. The first step of the render, this step here will be hit twice, because you'll start here, go here, hit that square model, make a copy of it. Then you'll start here, go here, hit that square model, make a second copy of it. That's how we end up with two squares, because we get to there's two paths in this graph to there. Since there's two paths, there's two copies made of that square in this first step, okay? Because you're going to iterate through the list of models, and you'll get to each model as many. Well, you can get to a model more than once. So you get to the model there, you get to the model there, but each time you get to the model, you make a separate copy of it. That gives us why we end up with two squares in our final scene. One square is going to be moved to that location in three-dimensional space, and the other copy is moved to that location in three-dimensional space. So it works out real elegantly. it's using graph theory, and it's using traversing of a graph like in an algorithms class. Essentially, I'm doing a depth first search, depth first traversal of this graph. It's doing depth first. So it's going down to there, then down to there. So it's doing a depth first search, depth first traversal of the graph. Okay, so that render is a depth first traversal of a graph now. Before, our render was just traversing a tree. Now it's traversing a graph. Yeah, in renders, in all the other renders, the scene was a tree. Now the scene is a graph, and we're doing a depth first traversal of the graph. Okay. Okay. So now we've seen, this why we're using matrices, and why we're using 4x4 matrices. So we've seen that we're using, the render uses 4x4 matrices. We've seen why and seen how. Okay. The next week, what we'll do is start looking at tricks for how do you actually make use of this stuff, and that's these examples here. Like, how do you get something like that to happen? Yeah. How do you rotate a square around a point like that? Or how do you do that? Or that? See, these are all slightly different ways of moving something around. Okay. So we want, how can I actually do these things? What kind of tricks do I, and that's what your last programming assignment is it's going to be to do these kind of things, to do to do some simple cases of moving a model around using matrices. So that's what we'll talk about, is to start, like, how do I use combinations of rotations and translations? And we'll see. This one only uses rotations and translations. There's one using is also scaling. See, the model's growing. That one's another one with a scaling. Notice it always rotates around the same point at the same time the model is growing. Okay. See, this one, as it grows, it translates around a different point. So there's all kinds of different little combinations of rotations, translations, and scaling that give you the effects you see in animations and games. So we're going to start looking at how do you actually do these. That'll be the last thing we do, is how do you actually make use of all this theory to get actual things to animate, to actually get animations.
The one that wiggled up the y-axis reminded me of Centipede from back in the day.
What do you mean back in the day? Is that a game or something?
Yeah, you never saw Centipede when, like, the arcade games were?
Oh no, I never played arcade games.
Yeah. It was
I mean,
really close to the way the Centipede moved.
Yeah, I predate those.
That one.
There were no arcade. There were only pinball machines when I was in high school.
Right.
There were only pinball machines. Yeah, but yeah, these things they're kind of fun. Yeah, actually seeing how to do these is a little bit interesting. Okay, so there's a whole bunch of animations here. To try to do these. How do you get these things to work? Yeah, and they're not a lot of code. It's each one is 4 or 5 lines of code. It's just once you learn a few tricks, there's a few tricks to this stuff, and you learn a couple tricks, and then you're just using the same couple of tricks over and over again to get all these different animations. Okay, so we've gone over, so I'll quit there. Oh, look for the homework assignment. It should be up there later today or tomorrow, and it'll be essentially examples similar to these examples here. I'll give you like a puzzle to do similar to these examples here. And the code you will need is in these examples here. Yeah. By looking at these examples, you'll see what you need to do. Like your homework exercise will be something that's a combination of a bunch of these things. Okay. So the answers to the solution to the programming assignment is these examples. You just have to see how to piece them together. You'll have to see how you piece them together to get the solution. Okay. And these guys are well documented. If you open one of them, they are pretty well documented. So they explain what they're doing. Okay. So if you start at the beginning and you read the examples in order, they build up the techniques. They build up the techniques that are needed. Okay, so should quit there. Gone over. Okay, so look for the programming assignment later today or early tomorrow. And if you have questions about it, send them to me. Hey, remember, next week is the last week of the semester. So there'll be an exam, and that's everything I'll put up in the next couple of days, is some problems for you. There'll be another exam like there was the first exam about this stuff here, about transformations. So I'll put up some review problems for that. Okay, so there'll be a programming assignment, and then there'll be a little take-home exam, like the first exam was on essentially matrices and transformations. Okay, all right. And
Professor, I had a question about the assignment. Are we still able to turn in like older assignments,
yes,
like we improve them?
Yeah, yeah,
okay.
Yeah, oh yeah, yeah. I haven't had time to grade them. Yeah, you've noticed you haven't got your grades. Yeah, yeah. If you've got improvements or if you haven't finished the homework assignment, yes, very much turn them in. Okay, so I'll accept them. You know, turn in anything that you haven't finished or resubmit something that you can do better. If you think you can do something better, go ahead and resubmit it. Okay?
Is there a definite deadline for those, or just like the?
They'll have to be, because I have to have time to grade them. So let's see. That's a good question. This is the last day of this semester. This is the last day of, this is final exam week, and grades are due this day here. That's the day grades are due. I probably need everything at the absolute latest by that Friday. And even then, I may not have time to grade it if I get it that late. Okay, so if you send me something on the 18th, I may or may not have time to grade it.
Okay, thank you.
Yeah, so the hard limit would be the 18th, because after the 18th, there's not much chance I'll have time to grade things. Okay, but that's a good, that would be a good target. Yeah, but the sooner the better, because I have to have grades by that day, and anything that's not turned in will be a 0. If you haven't turned it in by that day, it'll turn into a 0. Okay, so if you have questions about submissions, send me an email. But that's a good point. Yeah, I'm still accepting homework assignments. Blackboard or Brightspace, there's a due date, but it doesn't cut you off. I mean, I accept submissions, and I accept it's Brightspace accepts submissions as long as it's up there, and it'll accept multiple submissions. So you can accept something over and over again. Okay, so sometimes, I mean, I could set Brightspace up so that you can, you're stopped from submitting on a certain date, but that's not the way it's set up. So I'll still keep accepting things. Okay, anybody, any other question? Okay. Okay, so I'll go ahead and stop sharing, and have a nice weekend, and see you we'll meet again on Tuesday. Okay, bye.